Did you see I posted the weekly assignment? So that's due a week from today. I originally had 4 questions, but I took one off because when I did the solution, it was getting sort of long. So you're welcome for that. All right, so outline of thermodynamics so far. So I'm going to start out by just giving you a list of stuff that you can always use, although some of it has a simple assumption that you need to use. So in a way, I don't know, it's categorized kind of funny, I suppose. But like, for example, it says these are equations you can always use, but one of the categories is if it's incompressible. Well, you can't use it if it's not incompressible. But, okay, equations you can always use. So first, if the thing is a cycle, then the change in any property is 0. So this is for any property Q. Okay, so the first equation you can always use already requires that it's a cycle. Similar to cycles is steady state. You can think of steady state as just like an instant by instant cycle. And so first, you know that the derivative with respect to time of any property is equal to 0. So this is true for any property Q. And then second, you know that the inlet mass flow rate has to be equal to the exit mass flow rate, and you can just think of that as the mass flow rate. Third, if you have an incompressible material, first, you know that the specific volume is a constant. That's sort of like, think of that as the definition of an incompressible material. That also means that the density is constant.
Is that a big V? Or
No, little.
Would that also be big V?
Well, I guess if the size of your control volume isn't changing, big V. I think for control, I'm not sure, but this is definitely true.
Okay.
Okay. For incompressible materials, what do we know about the specific internal energy? We know that this is true for both ideal gases and incompressible materials, and this is a really useful thing to keep in mind. This only depends on the temperature. Third, the change in specific internal energy is equal to the specific heat times the change in temperature. Remember that it's only for incompressible materials where CV and CP are equal to the same thing.
So could you say that's the delta U is C delta T because they're the same? Or like as a con?
Yeah, I mean it comes from the definition that says, well, since U is only a function of T, C V is equal to du dt, and you can do the other one too.
Oh, and that other part, that other term in C, that other C falls out. Right? Is that?
Yeah, let's see. So CP is,
Because it's with the V constant or whatever?
yeah. The one I just wrote down is with the V constant. With the P constant, you get dH dt is equal to Cp, and so that's d dt of U plus PV.
And PV is constant.
PV, yeah, I guess PV is,
Right, because the derivative of the constant is 0.
yeah, but that pressure, I guess, yeah, the pressure just doesn't change with temperature because it's incompressible. And so, okay.
Thank you.
Yeah. And then the last one, this is an entropy one, says the change in specific entropy is equal to C times the natural log of T2 over T1. You can use these for any temperature range for incompressible materials. Remember, for ideal gases, you have to be careful about these simplifications, but here they work really for anything. Although you are limited by the phase changes on both sides anyways if you're talking about liquids. But that's just in contrast to when we talk about ideal gases, we have a bigger change in specific heats for over a given temperature range. And so you have to be more careful about using this type of calculation. Okay, fourth, for ideal gases. Well, first, you know that P little v is equal to RT. And this R is specific to a given gas. So don't make the mistake of using the universal gas constant there.
Is there any case where we'll be using the universal gas constant?
Well, you always have to use it to calculate that R if I don't give it to you, but that's the only time, yeah.
And that's the R bar.
We call it R bar, yeah.
And that's 8.314?
Yes, I think that's in SI units, yeah.
In kilojoules or in joules?
I think that's in joules because it's, yeah, I think that's in joules. I think that's SI units. Then what do we know about specific internal energy? I just said this.
It depends on temperature.
Yes, very good. It only depends on temperature. So for both of these, that's an important thing for both of these. Specific internal energy doesn't depend on pressure or anything like that. It only depends on temperature. Well, that also then means that specific enthalpy only depends on temperature, because you can, because it's equal to the specific internal energy, which only depends on temperature, plus you can replace the PV with RT from the ideal gas law. And so you just get this. CV. So now we don't have the one specific heat, we have the two of them. CV is equal to du d temperature. And so this lets you calculate that the change in specific internal energy is equal to CV times the change in temperature, but not if there's too big a temperature change. I mean, I call it a small delta T, but remember we've checked this out compared to the tables for ranges over 100 degrees Celsius, which to us seems like a pretty big temperature range, and it still comes out pretty well. But you have to be aware that that's getting less accurate as the temperature change gets bigger. Then what about CP? Well, CP is the HD temperature. And so if you use the one from C here, from part C, just plug it in and take that derivative, you get that this is equal to CV plus R. Then F, the change in specific entropy, is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And in the same one, I'm going to write the other equivalent one. And delta S is equal to CV times the natural log of T2 over T1 plus R times the natural log of V2 over V1. These are only for small changes in temperature. Why do these only work for small changes in temperature, but not small changes in pressure, small changes in volume?
Because the specific heats are constant?
Yeah, that's exactly right. So this is just an approximation of an integral, assuming that Cp, Cv, and R are constant. R is constant. It doesn't ever change. So Cp and Cv are the only ones that we're approximating at a given temperature.
And a small change in temperature is like 100 degrees Celsius?
Yeah, I mean, it really just depends what precision you need for your calculation. The higher that temperature range gets, the worse your precision is. But Yeah, let's call it 100 degrees. I think that's a reasonable. You can even get good ballpark figures for more than that. I'm pretty sure we did more than
that was like
yeah,
big.
right, and it still was pretty close percentage-wise, I think.
Yeah.
But yeah, and then you can think of that one we did earlier as just saying, okay, since it's incompressible, then we can skip that second term.
Mm-hmm.
Yeah.
Yeah, that's right. Exactly. And then G, for bigger changes in delta T, you can calculate this using stuff in the ideal gas tables. S0 at T2 minus S0 at T1 minus R times the natural log of P2 over P1. So you can use this for any delta T if you have a table for your material.
I imagine that probably almost every material in existence has a table at this point.
That's true, but we don't have a table for everything. So, but yeah, man, I was just I was doing the solution for the third weekly assignment, and our table didn't go into the range that we were using, and so I just Googled, like I just typed into Google, like I think it was entropy, specific entropy for whatever material it was at temperature of this Celsius and pressure of this bar, and the Google AI just spit out a number right to me, So, and I think I said on the weekly assignment, like if you don't have the tables for something, there's not a lot of stuff that you need tables for on the weekly assignment, but just get it online. Okay, so that's ideal gas. And I like ideal gas questions. So be ready for that, on tests and homework assignments. Fifth, okay, this is always true. The work of expansion. W is equal to the integral from the extensive volume at state 1 to the extensive volume at state 2 of PD extensive volume. And the easiest mistake to make is to do this calculation with specific volumes. Don't use specific volumes.
Could you do mass times
Yes.
this of specific volumes?
Yes.
With the mass in front?
That's right. You just need to know the mass.
With all three being specific?
Well, no, I mean, you have to, so if you have all your stuff in specific volume, which we usually do,
Yeah.
Then you just have to multiply everything by mass first before you put it into that integral.
Yeah.
But in that situation, though, then it would actually be d to the little v.
Oh, so you're,
I guess
so
this
you're
is
just
more of a
saying,
calculus question.
yeah, I mean, you're just saying, okay, so yes, you could do this as MV1 to MV2 PMDV.
Yeah.
Yes, you can do that's. I mean, that's what you're doing. I'm just saying, don't.
Yeah.
Notice that you don't want to plug your specific volume straight into that integral. You get the wrong answer. Okay, what do you need to solve this? You need pressure as a function of volume or constant pressure. The the simplest, sort of most natural way for me to make you do a work of expansion problem is to give you that relationship where pressure times volume to some exponent is a constant. And so anytime you see that, those polytropic processes, you can think like, I'll bet there's a work of expansion calculation coming up. But then also anytime pressure is constant, keep in mind, I mean, that's even better, you know. If pressure is constant, be like, okay, if I know the volumes, then I also know the work, you know. Okay, 6, the mass flow rate. Man, I'm glad I don't have another lecture today. My voice is going fast. M dot is equal to area of the opening times the speed of the fluid divided by the specific volume. Seven is the TDS equations. These always hold. It just isn't always practical to use them in this form, but in any process, these hold. So these say TDS is equal to du plus PdV, and those are all specific things. And the second one says TDS is equal to dH minus V dP. So now here are some ways to keep properties constant during a process. And the reason this is useful is in case a problem gives this as a hint for you to know that that property is held constant. Okay? So the first one is constant pressure. Anyone remember what the fancy word for constant pressure is? Isotropic is something else. Baric. Yep, like a barometric pressure. And anyone remember how you do a process with a constant pressure? It's a piston with a constant external force. So that can be a weight or, you know, applied through some other thing. But as long as the external force applied to the piston is constant and you're letting things happen slowly enough to always be in equilibrium, the pressure stays constant. What about constant temperature? Remember what the word is for that?
Isothermal.
Yep. And anyone remember how you do that?
Have a big enough reservoir.
Yeah, it has to be somehow in thermal contact with a reservoir, and it also has to proceed slowly so that there's time for this heat exchange to happen. So it has to be in thermal equilibrium with a reservoir. And it has to go slowly.
But you don't have to be putting any energy into the reservoir. That's not a requirement.
The idea is that this thing, that's one way to do it, is to keep changing the energy, keep adding or removing energy to the reservoir. That's how you, like a boiler, you keep shoveling energy into the fire, to keep it hot. But you can also just think of it, the idea of a reservoir is it's so big that your little changes to it don't affect anything. So yeah,
like the train example, like you're not changing the outside temperature by having this exhaust.
Oh, right. Yes, exactly.
Only that were true.
Yeah. It turns out over a couple hundred years you can change your reservoir. Okay, constant V. Let's say extensive volume. Is there, I guess that's isometric?
Is it?
Isovolumetric.
I'm going to say like the drawings.
Volumetric. And the way to do, so anything has a constant volume if the process happens in a fixed tank or any kind of fixed container. One important thing about this is the work of expansion is 0. And then D, no heat transfer. I don't know if I've even mentioned the word for that.
Cold. I did, I just don't know.
Adiabatic. And this is just insulated. Or fast. It takes time for heat to transfer. So if the material is moving through something quickly, it doesn't have time to have significant heat transfer. But usually insulated is the one that it'll say to tell you, okay, there's no heat transfer into or out of the system. And it doesn't necessarily mean cold, because you can have heat transfer out of your system too, into your system too, out of your system. Okay, and then the last...
But heat can be transferring through the system, just not in or out.
Right. But we're always assuming, I don't think there are any cases where we haven't assumed that things are happening in quasi-equilibrium. So things are happening slowly enough that at every instant we can assume everything is in equilibrium. So in that case, inside your system, there's no heat transfer happening. Well, I guess in control volume analysis, there's heat transfer always happening inside your system, now that I think about it. So yes, you are right.
Okay.
And then, what was that? 8. So number 9, the last one that you can always use, well, this one is for a fluid, so a gas or a liquid that's at rest and continuous. Then you always know that the pressure at the lower height is equal to the pressure at the greater height plus the density of the fluid times G times the change in the height, difference in the height. Okay, so next, the next big section is facts that are always true about simple compressible substances. What portion of this class have we spent talking about simple compressible substances? All of it. So everything that we talk about in this class is a simple compressible substance.
Incompressible ones.
What?
What about the incompressible ones?
Yeah, that still satisfies all of these. It's still called a simple compressible substance. I guess the same way that a function y equals 5 is a linear function, you know?
Yeah.
Like this category, simple compressible substances, is defined by how much you know about it, and incompressible is stuff you know even more about.
Okay.
Okay, so you just have to accept that.
Yeah.
Okay, so the first thing is they all have the vapor dome. So if you plot temperature versus specific volume, then a constant pressure process so this line is constant pressure. Looks like this. Over on the left side, you have compressed liquid. On the right side, you have superheated vapor. And inside the vapor dome, you have a mix. The point at the top is called the critical point. On this line, you have a saturated liquid. And on this line, you have a saturated vapor.
So that line is just a graph of all the points from a table at the saturated vapor
Yes,
point.
right. Yep, that's like table information right there. And, you know, different materials have different, like they wouldn't overlie each other, but that shape would be there for every material. Second, related to tables, well, it's, yeah, for using tables, you know that for compressed liquids, and superheated vapors, you need two properties to define a state. So if you know two properties, you can look up any other properties in that state. On either saturation line, you only need one property to define the state. So third, this is a pretty short treatment of this, but for linear interpolation, if K is your unknown, no, now I understand why I chose these letters. If K is your known property, and U is your unknown property, then U is equal to U1 plus U2 minus U1 divided by K2 minus K1 times the quantity K minus K1. And if you have to do this for a 2D interpolation, you just have to use it 3 different times. Okay, so this is kind of like a companion to the equation sheet. You know, this is stuff that you kind of want to always have available to you, be kind of in the back of your mind. Now we're going to get into kind of the course, like what we talked about part by part. So now we're going to like an outline of course topics. So the first one is the first law of thermodynamics. And we started with, so this first part A was for closed systems over finite finite time intervals. So this said the change in energy is equal to Q minus W. And it's often the case, you know, sort of look for reasons to believe in a given problem that this change in energy is just a change in internal energy. But remember, that's not a specific internal energy. So if you're doing everything in terms of specific internal energy, which we almost always are, you have to multiply by mass for that. And remember, when we did these kind of problems, really the only thing we were doing was getting used to the sign convention. where a positive Q means energy going into the system and a positive W means energy going out of the system. Second, we did closed systems, but in the differential form. And so I'm going to break this up into two pieces, I think. Computer. So the first one is the first law itself, differential form, that says dE dt is equal to Q dot minus W dot. And again, dE dt, often dE dt is equal to du dt. In fact, I would say, unless you have reason to believe that there are changes happening, significant changes happening in kinetic energy or in the height of the material, I would just always assume that this is going to be true. And then the second part of this, the main thing that we use with this differential form is heat transfer. And so I'll get those equations in here. For conduction, we have Q dot is equal to negative kappa times A times dt dx. And remember that for us, that negative is irrelevant, but it's always given, so get used to it being there.
And we're always going to use delta T over delta X?
Yes, that's a good point. Yes, this is always going to be delta T over delta X. Oh, one thing, put this next to heat transfer. The biggest challenge, I think, with heat transfer, it's largely just plugging values in, but don't trust the signs. Whatever signs you get out of the heat transfer equations, then you have to think about the direction of energy flow when you go to the first law. Everyone with me on that? You know what I mean by that? Conduction is like touching a hot pan. You burn your hand even though that part of the pan isn't over the fire. The fire heats up one part of the pan that heats up the next part of the pan, and eventually the whole pan is hot. Next is convection, no, radiation. This doesn't require medium, so that makes it special, different from the other two. It doesn't require a medium for transfer. And there's two forms of this equation. The first one says Q dot emitted is equal to the emissivity times the Stefan-Boltzmann constant times the surface area of the material times temperature to the fourth. This one by itself is not useful in the first law. This is just telling you how much heat something's losing, not how much net heat it's gaining or losing. The one that is useful is Q dot. This is like a net heat emitted is equal to emissivity times the Stefan-Boltzmann constant times the surface area times the quantity temperature of the body to the fourth minus temperature of the surroundings to the fourth. And remember that since temperature doesn't appear here as a difference in temperatures, this has to be Kelvin. And then third, convection. So Q dot is equal to a catch-all constant called H times the surface area of the body that's in contact with the fluid times the difference temperature of the body minus temperature of the fluid. Okay, any questions about any of that? Let's stop there. And then next time, we'll talk about the second law of thermodynamics. That's not true. What haven't we talked about yet? We still haven't talked about the frickin' control volumes.
So for that one, if I had like a microchip
Mhm.
and I wanted to be super specific, I would include the area of the face and then also the four sides if it was like
Yeah,
in the fluid.
that's right.
Okay.
So next time, control volumes and then second law. Okay.